So welcome everybody to part 2 of 3 of the Peters Group Math Exits. So today Sam's going to be defending his thesis. And most of you in here know Sam. Does anybody not know Sam? Jerry raised his hand. So Sam's a Pennsylvania native. Did his undergrad and master's like Gwen here. Sam's been very enthusiastic. Oh, see, should have waited.
You gotta start over now.
Sam, like me, has been a weather enthusiast for most of his life. Is that true?
That is correct.
Yeah. So, and Sam, like me, likes to storm chase, and he actually went storm chasing once this spring out into Ohio and Indiana and saw Supercell. So that was pretty fun. It's a lot of driving though. My mother-in-law came with us, and she really had a good time. So Sam's going to talk to you all today. Oh, before I start, Sam's been very active giving talks to the Weather Club and other sorts of, he even talked through Chaser Chat too, and Sam has, if you don't follow him on Twitter, I highly suggest that you do that. He has a lot of really excellent educational content about supercells, tornadoes, and all kinds of other weather phenomena. So Sam's really active in the sort of educational side of things, in addition to the really interesting research he's going to present today. So there's a theme amongst these presentations, and that is downdrafts. So Sam's going to talk to us today about the mechanisms that drive downdrafts in supercell thunderstorms. So with that, let's go into thesis mode.
Thesis mode.
Okay, do not control the rest of the lights.
Yeah.
There we go.
Thank you.
All right, thank you, John, for that introduction. I'd also like to thank the rest of my committee, Jerry and Matt, as well as my family for coming. I really appreciate that as well. So with that, I'm just going to get right into it. I'm going to be talking about supercell downdrafts, specifically the role that dynamic pressure accelerations play in creating them. So just as an intro here, what are supercell downdrafts and why am I so interested in them? First thing, supercells are deep convective storms that have quasi-steady rotating updrafts. And like other forms of thunderstorms, they produce localized downdrafts, which are downward moving currents of air. These downdrafts are capable of producing damaging winds at the surface as they hit the ground and are forced to spread out into a density current. And they may even be connected to tornado formation in supercells, as evidenced by numerous studies of these features called descending reflectivity cores. Tons of studies on those, kind of can go down a rabbit hole there. Despite their importance, though, supercell downdrafts, their dynamics have not been studied nearly as heavily as the dynamics of supercell updrafts. So I aim to kind of fill in some of that gap today. Oops. So just a little more about how downdrafts affect weather at the surface. So right here, we have a vertical velocity less than 0 in this storm here. And as the air comes down and is forced to hit the ground, the vertical velocity at the surface must be 0. We don't observe the atmosphere seeping through the ground, so obviously that must be true. And so as the downdraft hits the ground, it must spread out into the horizontal, and these horizontal winds can produce damage at the surface. And that's why we're so interested in these. So going further about what we know about supercell downdrafts at present, a study by Trapp et al. In 2017 found that the area of supercell updrafts was strongly correlated with the area of the corresponding downdrafts. However, they didn't really propose a dynamic mechanism specifically that was accelerating the downdrafts. Another study back in the 80s by Klemp and Rotuno found that specifically during supercell occlusions, which is this process where rain-cooled air sort of overtakes the low-level updraft, air may be able to accelerate downwards towards intensifying low pressure and create downdrafts. However, this mechanism doesn't really extend to other kinds of supercell downdrafts, and they tend to happen kind of sporadically, so it's not really a steady mechanism. There are also multi-Doppler radar retrievals of the 3D wind fields around tornadic supercells. One of these studies by Johnson et al. In 1987 found that downdraft trajectories began in the boundary layer to the east of the storm, ascended to 1 to 4.5 kilometers, and then descended to the west of the rotating updraft. That same study also presented some evidence that downward directed vertical perturbation pressure gradient accelerations, abbreviated VPPGA, and I promise I won't say the full phrase again, driving downdrafts, but they did not present a mechanism for the existence of this feature. A review article by Markowski in 2002 on hook echoes and rear flank downdrafts noted the limits of radar observations because these downdrafts tend to occur in areas of clear air, so it's difficult to get radar samples of what's going on in those regions of supercells. And so the general consensus among these articles reviewed by Markowski was that buoyancy accelerations were the primary drivers of these supercell downdrafts, though there were a couple of studies, including this Johnson study and one by Nelson in 1977, suggested that VPPGAs may also play an important role. But perhaps the most relevant study to what I'm going to be specifically doing was by Shankman et al. In 2016. They analyzed the vertical velocity budget of an outflow surge along a couple of trajectories in a simulated supercell storm. They found that the dynamic part of this VPPGA was the primary contributor to downdraft intensity. It accomplished this by creating high pressure to the west-northwest of the low-level updraft. They referred to it as sort of a stagnation point. I'm not a huge fan of that term, but that's what it's often referred to as in the literature. And I have a figure on the right here that from that paper that shows sort of the different vertical velocity terms decomposed. And what we're really interested in is this dynamic forcing, this red line here. You can see it spikes downward prior to the downdraft, and that's what's causing it to accelerate downwards. And they have a cross section here showing that pressure field as well. So you may be wondering, how am I going to go beyond this study here? A couple of things that I'm going to do that they did not. They looked at the vertical velocity budgets for just a few trajectories at a time. I'm going to be looking at very large sample sizes of downdraft trajectories and doing statistics on them. Secondly, they focused on downdraft surges that occurred over very short periods of time. I'm going to be focusing on sort of the steady structure of downdrafts in these supercell storms. Third, they did not decompose the VPPGA into its nonlinear and linear components. I will be doing that, and that's because I think doing so offers a better conceptual understanding of the processes that are going on. And lastly, they just looked at a single simulation of a supercell. I'm going to be simulating numerous supercells in systematically varied environments. So what are my research questions? I got 3 of them. The first one, what is responsible for accelerating the strongest near-surface downdrafts in steady-state supercells? Is it buoyancy? Is it this VPPGA? Those are kind of the 2 main things that it could be. Secondly, do these answers change if I vary the environment that these storms exist in? For example, if I vary the relative humidity below the cloud base, does that lead to stronger negative buoyancy that leads to stronger downdrafts? Or if I vary how the vertical wind shear in the profile, how does that affect the dynamics around the storm? And lastly, what are the physical mechanisms responsible for accelerating these downdrafts? So what did I think the answers were going to be going into this study? Well, firstly, I thought the pressure gradient was going to play a dominant role in these downdrafts, just based on my knowledge of how supercell dynamics work. The pressure field is often extremely important to their dynamics. In terms of varying the environment, I expected varying the low-level relative humidity to actually have very little impact, because if buoyancy doesn't play a huge role in these downdrafts, then the low-level relative humidity shouldn't either. And I also thought that stronger wind shear would lead to more intense downdrafts through stronger dynamic forcing. And lastly, what did I think the physical mechanism responsible for these dynamic accelerations would be? I thought it was going to be the linear term of the vertical perturbation pressure gradient acceleration. And that's due to the fact that supercell environments tend to have wind shear that varies with height. And just I'm going to give a quick conceptual primer on these linear pressure gradients, and then I'll go into mathematical detail later on. But just to start, supercells tend to develop in environments characterized by large and vertically varying wind shear. That lends itself well to vertical pressure gradients on either flank of an updraft. Really, the key thing you need to know for now is that high pressure tends to develop on the up shear side of updrafts, and low pressure develops on the down shear side. And so if you have a situation like this, where there's no wind shear in the lower part of the cloud in this east-west plane, but then if you go higher up in the cloud, there's large east-west wind shear, you'll get an area of high pressure here, no perturbation pressure beneath it, and so the air is going to accelerate away from that high pressure downward. And in theory, that should be in the region that we typically observe downdrafts and supercells in their rear flank. And so I thought this mechanism was a likely culprit. So how am I going to investigate this? I'm going to be using numerical simulations of supercells, looking at trajectories in bulk, very large sample sizes, and I'm going to systematically vary the environments that they exist in to see how that could impact things. So first, how am I going to be simulating these storms? I'm going to be using CM1. It's a cloud model that is often used in severe storms research. You may notice looking at this table on the right that has a few of the model parameters, that I'm using smaller vertical grid spacing than horizontal grid spacing. That was done very deliberately. When you're looking at vertical accelerations, I wanted as much resolution in that vertical as possible so I could accurately model how these accelerations were happening, because they can get pretty large. I used a technique called updraft nudging. It's fairly new, but has been gaining prominence to initiate a storm at the center of the model domain. And for microphysics, I use a Morrison double moment scheme. I do want to note that choice of microphysical parameterization can affect the cold pool characteristics of storms. This was found by Mersdek et al. in 2022. However, as we will see later, that likely is not super important to the findings of this study. So for our trajectory analysis, CM1 includes code that can solve for Lagrangian trajectories in parallel with the rest of the model. It can output various properties of these parcels, like its 3D position, velocity, and most importantly for this thesis, the different terms that contribute to its vertical acceleration. I initialized about 250,000 of these trajectories upstream of this updraft nudging area in areas that were expected to end up in supercell downdrafts. I initialized them in this blue box here from heights ranging from 0 to 5 kilometers above the ground. And the goal of these parcel placements was to maximize the sample size of these downdraft trajectories while keeping computational costs manageable. So the foundation of this thesis is going to be looking at the vertical velocity equation and the different terms that contribute to acceleration. This equation looks scary, I know, but really the only thing you need to know is that the vertical acceleration is going to equal a sum of buoyancy and the perturbation pressure gradient. Buoyancy contains a bunch of terms related to temperature, moisture, and condensate, but it's all getting lumped into this thing that we call buoyancy. And then the pressure gradient here. There are also some residual terms that get outputted by the model. However, I looked at these residual terms and they're so incredibly small compared to the other terms, they can just be thrown out. They're negligibly small. So how am I going to be varying the environments? There are two things that I want to vary. The first one is the lifted condensation level, abbreviated LCL. It corresponds to the height of convective cloud bases, and it's a good proxy for relative humidity in the lower part of the atmosphere. Higher LCLs promote more evaporative cooling of precipitation and production of negative buoyancy. Second thing I wanted to vary was deep layer shear magnitude. That's the change in the base state horizontal wind over a large depth of a cloud. Larger deep layer shear, I thought, may promote stronger dynamic VPPGAs for downdrafts, and that was my motivation for wanting to vary it. So going into more detail about how I'm going to be changing the LCL, I wanted to control for as many variables that could affect the storm characteristics as possible. So I constructed these vertical profiles very carefully to have constant CAPE, surface moist static energy, and upper tropospheric relative humidity. The reason I'm keeping moist static energy constant is because many microphysical processes have strong temperature dependencies. And keeping the moist static energy constant means that the parcel profiles of the updrafts will have similar temperature ranges. And so hopefully I'm able to mitigate those microphysical differences. The upper tropospheric relative humidity is important to keep constant because that affects the entrainment, the turbulent entrainment around these storms. So I wanted to keep that consistent as well. I used 3 values of LCL, 500 meters, 1,000 meters, and 2,000 meters. And this figure on the right just kind of shows how I was able to construct these. This purple line here is a constant saturated moist static energy. And these are temperature and dew point profiles, constructed so that when it reaches the LCL, it is following this line of constant saturated moist static energy. Next, moving on to the vertical wind profile, I used a piecewise function to construct vertical profiles here. In the lower part below the LCL, I'm using basically a quarter ellipse that is elongated in the north-south direction. And that's according to these terms here, this cosine and sine term. And then above it, I'm going to have straight east to west shear from the LCL to 5,000 meters above, and then a constant wind above that. So the C1 parameter, I'm going to hold constant across all these simulations at a value of 10 meters per second. People who are a little astute will note that a consequence of this is that lower LCL environments will have larger low-level shear and vice versa, just because there's a constant difference in wind over differing depths, so you'll have different vertical wind shear. I justified this by higher LCL environments generally having deeper turbulently mixed boundary layers, and thus suppression of low-level shear. And so I thought that keeping the C1 parameter constant was the most realistic way to construct these wind profiles with the varying LCLs. The C2 parameter, which I'm defining as the deep layer shear magnitude, and it will be referred to as such from now on, was given 2 possible values, 0.005 and 0.008. The units on those are 1/seconds. This is just a summary of the 6 different environments on skew T diagrams with photographs inset in the top right. On the going from left to right here, we're increasing the LCL height. So we have the 500 meter LCLs, 1,000 meter, 2,000 meter, and then going from bottom to top, we are increasing the deep layer shear. And so this row has the lower deep layer shear, and this top row has the higher deep layer shear. So how will I be identifying the downdrafts? I obviously need some kind of algorithm to identify these trajectories. I'm not going to go in and manually pick out thousands of them. So I need some way to do it automatically. I used 4 different thresholds to accomplish this. The first one, vertical velocity less than -5 meters per second. It had to occur at a height below 500 meters, and it had to occur at least 40 minutes into the simulation, also within some horizontal constraints given by this blue box. You can imagine this is the 200 by 200 domain. They had to occur within this blue box. So why these requirements? First off, the vertical velocity threshold was picked to filter out the weak downdrafts while still maintaining a large sample size. I found -5 meters per second was a nice round number, and it also was kind of a sweet spot for accomplishing this. Picking downdrafts with a height below 500 meters was done because I'm interested in the near surface downdrafts, because those are the ones that most directly impact weather at the surface. I had to pick out downdrafts after 40 minutes of model time because this updraft nudging process that I was using to initiate the storms takes some time to spin up the steady state supercell structure that I wanted. And so I wanted to give ample time for those processes to happen before I started sampling these downdrafts. And lastly, these horizontal constraints were done to ensure that the downdrafts were only associated with this primary right-moving supercell that I was interested in. And I kept these constraints consistent across all 6 simulations. This is just showing this is the right moving storm that I'm interested in, and this is a left moving storm that I'm not interested in. So this blue box was drawn to delineate between the two. I also want to note that minor changes in these thresholds yielded qualitatively identical results. And so I basically just picked the values to maximize sample size and include really weak downdrafts. So now getting into some of the results, I want to start by just some general supercell characteristics. 5 out of the 6 simulations yielded a steady state supercell with updraft velocity that was steady throughout the simulation. The other simulation that did not, which had the lowest LCL and the weakest shear, exhibited transient supercell structure while slowly decaying over time. That's this red line here. You can see its updraft is steadily decaying over time. Also in this plot here, I have this dotted line, which corresponds to the theoretical vertical velocity from Cape. So nearly identical steady state updraft intensities throughout all the simulations. And that says to me that I did a pretty good job controlling for all the different thermodynamic variables, that constant moist static energy. I was able to keep these updrafts pretty consistent across some widely varying environments. So now getting into distributions of downdraft vertical velocity, despite varying the environments, the distributions were pretty similar. Here I have just have histogram plots, and then these lines correspond to different percentile thresholds. There are some differences, however, none of the differences were consistent across, going across a whole row. So there's kind of like no rhyme or reason to why some had more intense downdrafts than others. Now looking at the heights of these downdrafts. So this is a plot showing the progression of the height of these downdrafts. And what I've done is I've normalized it by LCL height. Basically, I've taken height of the parcel and I've divided it by its LCL just to put it in terms of like storm relative height coordinates. On this x-axis here, these are the minutes prior to the downdraft. And so this 0 point here corresponds to when the downdraft threshold was reached. I go out to 15 minutes before the downdraft and then 5 minutes after the downdraft. And so you can see that most of the downdraft trajectories, this is the middle 50%, this middle blue shading here. Most of them began below their environmental LCL height. They then slowly rose to around the height of the LCL, maybe even a little above in some cases. And then they experienced a large downward acceleration that brought them very close to the ground. And so this says that accelerations happening around or just below the LCL height must be particularly important for these supercell downdrafts. As for their locations in the horizontal plane, I have a plot here showing basically a snapshot of radar reflectivity simulated by the model. And then these black dots correspond to downdrafts that occurred. And what I've done is this center point here on each of these panels corresponds to the location of the 5 kilometer updraft. So what these are showing is where these downdrafts occurred relative to the storm's updraft. The strongest downdrafts routinely occurred in these clusters to the west of their parent updraft. You can see that's consistent across all 6 of these simulations in what most people would refer to the rear flank region of the storm. Accelerations, therefore, happening in these locations to the west of the updrafts must be particularly important as well. Now I'm going to get into the vertical velocity budgets. This is the really good stuff. These are plots of the vertical velocity budget. Here in blue, this is the vertical pressure gradient term. In red, this is the buoyancy term. And in black, I have added the two together to show the net acceleration. I also have percentile ranges here to show some of the spread of the distribution. And these dotted lines correspond to the time when the downdraft threshold was reached. This x-axis is the same as the parcel height plot before. The first thing you can notice is that these are all qualitatively very similar. The similar magnitudes of downdrafts, and they occur over similar periods of time as well. I'm going to zero in on this panel E here and just sort of go through a typical evolution of these supercell downdrafts. So they begin in hydrostatic balance. You can note that the vertical acceleration is close to 0. And so these two terms are in approximate hydrostatic balance. Next, about 5 minutes before the downdraft threshold is reached, the trajectory may slightly ascend. You can see very small upward accelerations across some of the downdraft trajectories. And then in the 5 minutes leading up to the downdraft, this vertical pressure gradient, this green line here, is rapidly reduced, while the buoyancy is still at its negative value. And so when you add them together, you get a large downward acceleration, negative value here. That throws the trajectories wildly out of hydrostatic balance, and they are forced to accelerate downward. During the downdraft, buoyancy may even slightly increase due to some adiabatic processes. It's pretty minor, and it's also not really present in the high LCL simulations. So whether or not that happens may depend on the thermodynamic profile. Immediately following the downdraft, the VPPGA spikes right back up. This actually must happen because of what we talked about earlier. As the downdraft must decelerate to 0 before it hits the ground. And so this is basically acting as like the brakes to slow that downdraft down. And then they return to hydrostatic balance near the surface immediately following the downdraft. Now I'm going to get into some statistics here. So this plot is basically a 2D histogram. What I've done is here on the x-axis, this is the minimum value that each of these terms achieved. And then on the y-axis, I have the minimum vertical velocity that occurred after that. And so I have the two terms of interest, the vertical pressure gradient and the buoyancy. And then on the right, I've added the two together to sort of approximate the actual acceleration that they experienced. And so across all of the simulations, the vertical pressure gradient exhibited a much larger correlation to the eventual downdraft intensity in comparison to buoyancy. You can see a much larger correlation here. And in fact, in 5 out of the 6 simulations, the buoyancy actually had a small negative correlation, which was interesting to see, though the magnitude is pretty small, so it might partially be noise. Adding the vertical pressure gradient and the buoyancy together only marginally improved the correlations. You can see it's actually not equal to 1. I can explain that later if someone wants to ask a question about that, but it does make sense, I promise. So what is causing the reduced VPPGAs? Well, we've learned from these spatial plots that there are that any possible mechanism must occur to the west of these supercell updrafts, and also must occur around the height of the LCL, maybe a tad below. So now I'm going to get into some of the mathematics of the vertical pressure gradient. So we're going to begin with an equation for perturbation pressure. Now there are a bunch of complicated terms, but basically I'm going to turn it into a nonlinear, a linear, and a buoyant contribution term. I'm going to denote that as the forcing F and subscripts here, just to denote which one we're talking about. I have a table here that explains sort of in more detail what each of these terms mean, but it's not super important for this presentation. Next, we're going to take the vertical gradient of this equation, multiply it by -1, and we're also going to assume a constant reference density, basically like a Boussinesq approximation, which allows it to be moved totally inside the Laplacian. The reason we're doing all of that is so that we can get the term to look exactly like this inside the parentheses, because that is the vertical pressure gradient acceleration. And so basically we turn this into an equation for the VPPGA, and we get this thing at the bottom here. For the purposes of most analyses in severe weather with this equation, the Laplacian can be thought of as being proportional to a negative sign. And so we'll do that there, and we get this proportionality here. So the VPPGA is proportional to the vertical gradient of these forcing terms. And so in order to contribute to a negative VPPGA, which is what we're interested in accelerating these downdrafts, these forcing terms must decrease in magnitude as you go up in height. And so what I've done is evaluate the linear forcing on these storms. These plots are going to take a couple seconds to explain. This is the same domain as I showed with the downdraft locations earlier. So these center points correspond to the 5 kilometer updraft. What I've done is at the height of the simulation's LCL, I have calculated this linear forcing term. And then what I've done is I've composited these plots together over a period of about an hour. So this is showing the steady state structure of these storms. It's not a particular time. This is a time average of the storm structure. These blue values indicate forcing for downward accelerations, and the red indicates upward accelerations. And so doing this reveals that we have these downward accelerations exactly in the right spots to explain the downdraft clusters that we saw earlier. They're consistently just to the west of their parent updrafts. The nonlinear terms I also calculated, but they became very small after doing the steady state compositing. Maybe I calculated them wrong, but I'm pretty sure I didn't. So I feel like they are unlikely to be responsible for the steady state downdraft structure. They may be very important on smaller time scales, but for the time scale that I'm interested in, they don't seem to be much of a factor. These linear forcings were also larger in the higher shear simulations. You can see a deeper blue here than down here. These are using the same color scales. Though apparently this did not contribute to significantly stronger downdrafts, I may not have varied the correct part of the vertical wind profile. Maybe the lower part of the wind profile is more important, but that is something to investigate later on. Now I want to get into how this could possibly be used operationally, because the fact that the linear term of this VPPGA is important is really good news, because that's possible to estimate from environmental soundings. So what we're going to do to accomplish that is start with this linear forcing term here. Next, we're going to expand the right-hand side using the product rule. It is just a derivative after all, and so it follows those calculus rules. Next, what I'm going to do is approximate the vertical velocity as increasing linearly with height. This may seem insane, but I promise you it's not. I have a vertical profile of updrafts that I've composited across all my simulations. And you can see this red line corresponding to a linear increase in vertical velocity. It's not that bad. It's actually okay. And so that's just a little justification there for an approximation that may seem crazy at first glance. So after some manipulation and plugging that approximation into the equation, you can show that the VPPGA as a function of height should be proportional to this thing here. And this term in parentheses here is what we're going to evaluate on these vertical profiles. It's essentially the sum of the vertical gradient of the shear times the height plus the shear. And the shear is just the vertical gradient of the vector horizontal wind. So this formula is pretty straightforward to calculate from a vertical profile of U and V, the east-west and north-south components of wind, using finite difference methods. I have done so on 2 of these soundings. Some of you may recognize these soundings in particular. They're pretty famous ones. And so I propose that this technique may be able to predict the potential strength of steady supercell downdrafts. Basically, this profile here at the bottom has larger linear forcing and may be more capable of producing strong downdrafts than the top profile. So to summarize, I used a matrix of 6 supercell simulations in environments that were systematically varied in order to fill a gap in understanding of how exactly these supercell downdrafts accelerate. Through analysis of Lagrangian trajectories, I found that varying the LCL and deep layer shear did not appreciably affect downdraft intensity. Downdrafts experience their largest downward accelerations around the height of the LCL and just to the west of supercell updrafts. These accelerations were driven by sharp reductions in the vertical pressure gradient. The minimum in that vertical pressure gradient was found to have a much stronger correlation to eventual downdraft intensity than the minimum buoyancy. And then I also presented evidence for the linear dynamic mechanism being the primary driver of steady state supercell downdrafts through a reduction in the VPPGA in the rear flank region. So now just going back to my research questions, just to make sure I actually answered them. The first one, what is responsible for accelerating these near surface downdrafts? Answer, it's reductions in the vertical perturbation pressure gradient, almost exclusively. Secondly, do the answers change in different environments? I varied the LCL and the deep layer shear, and it did not influence these downdrafts in a meaningful way. Third, what are the physical mechanisms responsible? Linear dynamic forcing is the primary mechanism for these steady supercell downdrafts. Avenues for future work, looking in particular more at the unsteady downdraft structure occurring over shorter timescales forced by these nonlinear vertical pressure gradients. I think that would be very interesting to investigate. And also what environmental parameters, if any, actually impact the downdraft intensity the most. And this picture, I just want to finish with this. This picture that you've been looking at the entire time, it is a linear force supercell downdraft. So I saw this on a storm chase in PA back in April. I was very pleased to see this for very nerdy reasons. So this linear dynamic high pressure here, an acceleration down that clears out some of the clouds. Very cool to see in person. And with that, I will take any questions. Thank you.